Okay, great. So welcome everyone for, I guess, our first Zoom quantum seminar of the program, but we'll have these every Tuesdays. As we discussed earlier, the time might move to 10 a.m. PST to accommodate people in Europe, but I'll send an email about that. So today we're happy to have Chris Schaffner from Amsterdam, and he's going to tell us about, oh, and so I can see that Chris used to do the slides from IFKE. So Chris is going to tell us about work with IFKE Dulek, who's also in the program, Alex Guido, who's in the program, Stacy Jeffrey, Christian Machens, and himself. And so he's going to tell us about secure multi-party quantum computation. Okay, so
all right,
Chris, and feel free to ask questions.
Yes, thank you very much, Thomas. So I cannot see your faces, but I think you can see mine. So I'll try to smile from time to time. So as you just said, this is joint work with a lot of people. And also that's the second slide. So see, like I haven't changed much. And I would already in the first slide thank IFKE for making basically all the slides. I only changed the epsilon fraction of them. So thanks a lot, IFKE. So we're going to talk about multi-party computation for this hour. So multi-party computation is when a bunch of people come together and they want to compute something together. So in this example, everybody has an input, say some numbers, and they want to figure out, for instance, who has the biggest number. You think of salaries, think of like fortunes. Now in the millionaires problem, people want to figure out who has most money. And so that's their input. If we had a trusted third party in the middle that everybody trusts, the players could simply just send all the inputs to that party. The party would compute this function and output the output. So in this case, they could figure out what is the largest number, say 102, could announce that to the players, or maybe even better, she could kind of compute individual functions for the players and just send back, for instance, yes, you are the one with the highest input, or no, you are not. That would even further minimize the amount of information the players learn. So that's what we want to achieve. An example, this is the ideal situation we want to achieve in multi-party computation. But of course, in cryptography, we are concerned with the setting where we don't have this trusted third party. So what we can do instead is we can come up with protocols that try to emulate this situation. Is there a question somewhere?
We're still seeing the title slide here.
Oh, really? Is this the case with everybody?
Yes.
Okay. Then this is not good. Let me see if I can fix it. It's good that you tell me before I went through all the whole talk. So let me try to share this again.
Yeah, so it looks, it's moving now.
Oh, but it says sharing is paused.
Well, it's not. Try to move it so we can see if it moves.
Bring your shared window to the front. What does it mean?
So it's not moving now. It moved like once, and but it stopped.
Interesting. Maybe I should let me remove the speaker screen. Maybe this will help.
Maybe you can first go to presentation mode and then share. Maybe it shares something different in that case.
That could.
I mean, it could be a separate windows in which it shows the talk for some reason.
I have now unplugged. I have a second screen, and it still says sharing is paused. Strange.
But did you do what Norbert suggested, which is first start the presentation and then click on share screen?
In fact, then I wouldn't know, then there is no thing to share the screen. No. If it's on full screen, then I cannot share it. So right now, I guess you see the closed screen. So now it says sharing is paused.
Okay, but why? Anyone has experience with this?
I don't know. I mean, I would switch now to Zoom, which I don't know how it works on Macs or whatever, but and then try to share from there, because now this window should be open, which the presentation runs.
Can you do like on the Windows
fine.
you do Alt Tab to switch to Zoom?
Exactly.
Yeah, but it doesn't do that.
I mean, I know that on Linux, typically presentations run in kind of separate windows, the full screen part. So if the sharing shares a specific window, oh.
So you see the flowers now?
Yes.
Yeah.
Okay, that's a good sign.
Whoa.
How did you do it?
Well, so I'm sharing my desktop instead of the so my only question is this gray box back?
No.
No.
Okay. No, then I
Flowers are gone.
Okay, so it seems to be working.
Very good. Okay.
Okay.
Well,
Great.
sorry for
everyone.
for the trouble. So okay, the trick is to share your desktop and not the Keynote application. Right. So Yvke, thanks a lot for your slides. Here are the flowers because you haven't seen them before. Multi-party computation I just explained. So here is the example now with actual numbers. Everybody has every player has an input xi. If we had this trusted third party, let's call her Shafi, for instance, somebody we all trust. She could actually just compute this function and send back the answer. She could even compute individual functions for every player as inputs of all as function of all the inputs, and inform the players about the outcomes. And that's what we ideally want to emulate with a protocol. So a protocol here is sketched just as a form of interaction between players. In fact, not all the arrows are drawn here. In fact, all the players can talk to each other in a protocol. And we still want to do the same thing. So what we want is we want to achieve so-called input privacy. And that means that basically the inputs of the player should be hidden beyond what they will learn anyway from the outcome of the function. And this should hold even in the case if we have adversarial players. So even if some players are misbehaving in the sense of not following the protocol, it should still be guaranteed that these players, even together, cannot learn the inputs of honest players. So that's one thing we want, but the other thing is what we want to achieve is correctness. So that means, well, if everybody is honest, then everybody should receive the right output. But it should even be the case that if we have adversarial players like on this picture, then it should still be guaranteed that the honest players are receiving correct output, so the function evaluated on actual inputs. But of course, there's a few things we cannot prevent in this case, namely that dishonest players could simply lie about their inputs. I mean, it's not even fully defined what it means for them to have an input, or they could just behave in some arbitrary way, dishonest way. But nevertheless, no matter how they behave, there should be some input that's kind of assumed for them. So that's how they participate in the protocol. And the evaluation of the correctness still requires that the correct function is computed and given to the honest players, even if they lie about their own inputs, or if they provide different kind of inputs to dishonest players. And there's another problem. If you assume that we have more dishonest players, like in this case, say 4 out of the 6 players are dishonest, then there's an issue that they can basically simply just walk away once they have seen enough. So there's something that we cannot avoid, and this can actually be formally proven, that dishonest players can simply abort the protocol, and this can be kind of unfair for honest players, because it might be that they already have learned their outputs, but if they don't like the outcome of the protocol, they would just abort and walk away. So that's something we cannot avoid, and we basically just have to live with that. Sometimes these protocols will simply abort. So what we want to do in this talk is the quantum version of all this. So what we call quantum multi-party computation, or MPQC, so multi-party quantum computation. So there's always the constant confusion of where exactly we put the Q, but I think we settled on multi-party quantum computation. And the setting here is as follows. So do you actually see my mouse pointer?
Yes.
Okay. So we assume that all the players have some quantum state as input. So in principle, they hold registers R1 up to R6 in this case, and they want to perform some arbitrary quantum computation on these inputs. So in this protocol, in this talk, I'm going to present you a protocol for doing that. And here are kind of the parameters we're going to achieve. So if you call k the total number of players, then actually we'll be able to tolerate up to k minus one adversarial players. So it can be like in the extreme case, there's really just one honest player in this whole protocol, and kind of all the rest are playing together against that person. And nevertheless, you want to have some security guarantees in that case. Then what we do is we settle for computational security, but I can already tell you now that in fact, everything we do is kind of an information theoretic upgrade from whatever comes from the classical multi-party computation that we're using under the hood. So all the computational assumptions in this talk are basically hidden in the classical multi-party computation part. Furthermore, what we're going to do is we're going to kind of get to this protocol, build this protocol basically gate by gate. So basically I will show you how to do particular types of gates. And in the end, we're going to end up with a protocol that takes a certain amount of rounds. So the round is basically k times d, where k, as I said, is the total number of players, and d is the form of depth of the quantum computation we want to perform. And in particular, it's the CNOT and T depth of the quantum computation. So for those who don't know what that means exactly, you can just think of like the total number of gates that is performed. But basically, it's kind of if you layer them, then D is the CNOT and T depth of this computation performed. We're going to make heavy use of classical multi-party computation. So we just simply assume that we have a trusted third party, Shafi, that she's going to help us with all of the classical computations we have to perform. So that's the goal. Normally now I would look at the audience and see if I see any question marks in the faces, but I can't. So please let me know if there's any questions so far. If nobody is saying or raising its hand, then I assume everything is good. So I will quickly sketch what previous approaches have done to achieve multi-party quantum computation. So the first one is using secret sharing. So this is similar to the kind of classic MPC protocol, like the BGW style protocol, where basically players share their inputs. So how does it work? So this has been suggested by Crépeau, Gottsman, Smith, Benor, Hasidim, Smith, came later with an upgrade. But the basic idea is that you take input, say, player one holds a quantum state, this blue dot, and what he's going to do is he's going to split this quantum state up in shares. So basically do secret sharing of this quantum state, and you distribute that to the players. So it's the kind of the classic distribute and compute paradigm that is often also followed in classical multi-party computation. And so you might have dishonest players, but they, even if they kind of don't follow what they're supposed to do with their shares, as long as you have enough other players, then kind of the information about player one's input is still there. So you can work with that. However, you also see the problem already here, say, assuming you have 3 dishonest players out of the 6 in total, well, then you will have a problem, because in fact, now if you have more than half of the player or half or more of the players corrupted, well, then it's actually in a quantum setting not possible anymore that both the sets now of honest players and dishonest players hold the whole information about the quantum state, because obviously that would contradict the no cloning theorem. If you were able to extract the whole state out of the 3 shares of the dishonest players and the 3 shares of the honest players, then you could actually clone the state. So one gets into trouble with this approach if basically more than half or more of the players are dishonest. So this works for a strict majority of honest players. Then the other approach that has been suggested so far for the setting of multi-party quantum computation is the so-called DNS approach of the Dupuis, Nielsen and Salvail. And they basically looked at the 2-party case. And they use a different kind of technique, namely they use quantum authentication codes to protect the inputs. So they basically assume that, or they show how to encode players' input so that once this input is kind of sent to other players, in particular to dishonest players, it's protected. So even if they try to do something to this input, then they're gonna have a hard time. So because of the authentication code. And the hope is, of course, because so they can they do 2-party computation where they can tolerate 1 dishonest player, so which is already half of the players. So the hope is basically, if one generalizes this approach, then maybe it's possible to tolerate up to k-1 dishonest players. So that's basically the approach we are taking here. But we will do some additional upgrades to this scheme that was proposed by DNS. And in order to explain all this, I will start off with telling you a little bit about how to authenticate quantum states. And basically, if you're watching this on video, you should pause your video now and click on that link and go back and watch Yvke's tutorial from the bootcamp about this. Because all that I'm going to say on this slide is actually just a recap of what she's been explaining in more details there. So what we're going to use is the so-called Clifford code. So the key is an element from the Clifford group over n+1 qubits. So this is a subgroup for all possible unitaries you can perform on n+1 qubits. The Clifford group is generated by the Hadamard transform, the square root of z and CNOT. And the good thing is that it looks random. So basically, applying a random Clifford operation basically randomizes your state, and in a sense also encrypts your state. So here's how the encoding works. You take your, so this is a single qubit. If you want to encode this into the Clifford code, what you do is you simply attach some so-called traps. So just 0 qubits in a 0 state, n of them. And you apply the C, the key, which is just a Clifford operation on these n+1 qubits. And in order to decode, you simply apply the inverse of C, so C dagger, and then you measure the traps. So you check whether the traps are still in the all 0 state. And one can then show a theorem or can make kind of security claims for this kind of code. And informally, one can prove that if an attacker comes, so for any A, an attack on n+1 qubits, the probability that A changes the data qubit psi, but is not detected at decoding, so not setting off any traps, this is actually very small. So that's the reason why this is a good way to encode qubits. And if you want to know, well, what I said before, the Clifford code also provides privacy. This is not a coincidence, because actually in the quantum case, one can show that if you have an authentication code, then actually it necessarily also has to encrypt. And if you want to know more about this, then you should really go back and watch Yvke's tutorial from the bootcamp. So far, so good. Maybe somebody can say yes or click on yes, because I'm feeling kind of alone here.
Yes.
Great, great. Let me see. Okay, there are 23 people listening. Good. All right, so next, let's use this Clifford code in the multi-party quantum communication protocol, quantum computation protocol. So let's say people encode their inputs into the Clifford code. I'm gonna tell you a little bit more how to actually do this. Well, immediately you see there's some trouble with that. Well, how can we be sure that dishonest players actually do this properly? You know, they're trying to disrupt this whole thing. So how can we make sure that they actually properly encode their input into the Clifford code? Another issue is, I mean, once you have authenticated quantum states, I mean, they are protected from being altered. So on the other hand, we want to compute on them. So like, how can you actually do this? So this seems to be like contradicting. And the answers to like both of these questions is, well, we're gonna ask Shafi to help us. So we are gonna use classical multi-party computation to solve these problems. So the first idea is basically, so like, how could we encode these quantum states in the Clifford code? So if you kind of do a straightforward generalization from DNS, so what they do is, well, let's say the first qubit of R1 gets encoded into the Clifford code as I outlined. Now send this to the second player. Now the second player is just gonna put another encoding on top, in the sense of like what I describe here, just add another n trap qubits in a 0 state and apply a big Clifford, like a bigger Clifford operation on top of this. So notice now that we not only have n plus 1, but we actually have 2n plus 1 qubits in total. So this will have the following effect. For R2, these second trap qubits are kind of accessible because, I mean, he just applied C2 himself. On the other hand, he doesn't know what C1 is. And so these first player's trap qubits kind of are inaccessible for him. So it will be difficult for him to check whether the first player has actually properly put 0 traps here. So here's the first place where we can ask our classical multi-party computation for help, because we'll assume that the classical MPC knows C1 and C2, basically all these operations there that are applied. So what we could do is we could ask the MPC to kind of provide us with a description of this operation, which would undo C2. So let's say we take this state here and apply it to the state we have. This would undo C2, it would undo C1, and then we can basically choose which of the trap qubits we want to reveal. So for instance, we could kind of reveal now player 1's trap qubit and could then test those. So with the help of the MPC, we could kind of change the state into something where we can make these new traps accessible. And you can imagine that you can continue this. And so if you do this in the whole round and this state goes around, then it will just grow. Every time n trap qubits are added and a new big Clifford is put on top. So I think this would work. Now, of course, one would have to prove that it actually does, but the obvious drawback of this is that the ciphertext, so the encoded quantum states, they just increase with the number of players. So basically, just to encode one player's input, you will end up with n times k, or n is a security parameter, and k is the number of players, plus the qubit that you wanted to encode. So, so that's not what we're doing, but instead, and we invented basically a so-called public authentication test to get around this problem. So how does this work? Well, let's take this first player's input. So what we're gonna do is we're gonna send this around, but now, so maybe, so instead of adding n trap qubits in the 0 state, what we're gonna do is we're gonna add 2n 0 state trap qubits. And then we simply just send that state around and have all the players apply a Clifford operation on it. But this Clifford is now from 2n plus 1 qubits. So in this case, the ciphertext or the encoded qubit state does not grow, it just remains 2n plus 1. And in order to analyze this, so we're going to call this big operation C. And nobody knows that because they've just applied their own individual Clifford. And the traps have been inserted by the first player. Now we're going to ask Shafi to help us, because what she's going to do is we're going to kind of do some randomized check on these traps. So what we're going to do is we're going to select a random function. So this is this G is basically, you can think of it as a binary matrix of size 2n by 2n, which is invertible. And if you have such a thing, well, then this function, it will actually only output 0 if and only if the input was 0. So it's kind of a 0 test. And the high-level idea is to basically apply this random function G on this trap part, which has size 2n, and we're going to measure half of them. And the fact that it's picked at random, it kind of tests randomly half of the position. It actually does almost the same as testing all of these traps. So what we're going to do, this was just a high-level idea. Concretely, the MPC is going to compute this operation here. And we're going to ask player 1 to apply that. So pick a random string R and pick basically a random Clifford of n plus 1 qubits C prime, and then ask the player 1 to apply this operation. So this is just given to player 1 as one big Clifford operation. And you can easily see what happens if it's applied to the state. So before that, so what is going to happen is, like, you're going to undo the C, you're going to apply the G part, so this randomized operation on the trap part. You don't do anything on the data qubit, and then you actually kind of put a one-time pad, so you randomly flip the last n qubits, and you kind of properly encode the first n plus 1 qubits. So the next step is to ask player 1 to measure the last qubits and check if the outcome is 0. Well, that was before applying the one-time pad, or kind of the randomization. So now you should check that the outcome is R. So that's the procedure. And the result, what we can prove is that indeed, if this checks out, then the player is going to end up with a kind of properly authenticated quantum state. So then the C prime from here is going to be applied to the data qubit, and basically traps that we have now verified that they are 0. So the advantage of this public authentication test is that only one player actually performs the test. So he applies his Clifford, he measures, and all players can verify the test through the classical MPC. The fact that the MPC knows what's going on and knows this R, that makes this test kind of public. So this test will be used in different stages of our protocol. For instance, it can be used to test encodings. So that's what was the original motivation, like that players have properly encoded their input. But we'll also see how to use this test to kind of verify that the computation step has been executed honestly. All right. I'm going to go on and describe kind of the computation part to you. And maybe, yes, maybe it's a good time to ask questions. Exactly.
Yeah. So, so it seems like any player can cause that authentication to fail by, I mean, if they do anything, when you pass it around, right? If any player does anything.
That's correct.
And so there's no way to identify who was the problem.
No. So what we do, there's no kind of, sometimes in classical MPC, they call this traitor tracing. So kind of have an idea like who acted wrong, or they would even like accuse each other. And so, you know, one of the two is the one, it must be dishonest. In our case, it's simply if something goes wrong, we will abort.
Okay.
And I think this can be somehow justified by thinking of like the extreme case now where there's really only one honest player. So then anybody else is possibly dishonest. Any other questions at the moment? So I've kind of given you an idea of what we want to do. I've talked a little bit about authentication. I presented you this public authentication test. I'm now going to describe you how to do the computation steps. So basically what we want to do is we have these properly encoded qubits, either inputs, but also this kind of can be states that are intermediate states of the computation. So, and what we want to do is we want to apply gates to it, and certain types of gates. So I kind of split it up in 4 different cases. But basically, we want to end up with again a properly encoded state. So now maybe under a different Clifford, like C prime, but this gate should be applied to the data qubit. That's our goal. And so there, I'm going to talk about 4 different classes of gates that we want to apply. The first one is 1-qubit Cliffords. The second is going to be CNOT, and then some non-Clifford operation, and finally computational basis measurements. So let's start with the first one. That one is easy, because if you want to apply only single-qubit Cliffords, so let's focus on one of the states here. It's properly encoded. What we're going to do is basically we're not going to do anything quantum. We're just going to ask the classical MPC to kind of update the key. Yeah? So the classical Shafi, she knows all these Cs. Now these are the keys of the encoding of all the players. And if you want to apply a single qubit Clifford gate, this G to it, what we're going to do is we're going to just simply ask Shafi to change the key that she remembered from the original C to a C prime, where C prime is defined as this original C, well, like the identity times the gate we want, the inverse of the gate we want to apply, and the original C. Because if we do that, then we can easily verify that once we decode, then this blue state here will decode to the inverse of this new key. And so if you kind of plug it in, well, we will undo that Clifford, and then we'll actually apply the gate that we want. So we will end up with the right state, and we simply achieve that by like not doing anything on the quantum level, but just basically update the key that the MPC remembers. So that's kind of an easy trick to handle that case. So far, so good. Right. Then the next case is CNOT, and that's a bit more tricky because now we have to handle 2 qubits, and they are both of them are properly encoded. And if we just try the same strategy as before, kind of do the inverse CNOT and then the encoding that by just updating the keys, well, that will not work because this is not kind of properly encoded anymore. It's not in this product form that we need in order to continue our computation afterwards. So on a high level, instead, what we're going to do is we're going to ask player 1 to perform a computation, and that's going to be this computation. So it's basically undoing the Cliffords of the encoding. Remember, Shafi knows this encoding, so she can cook up this operation. She can choose freshly random C1 prime and C2 prime, and then kind of give just this big operation to player 1 to perform. So basically undo these Cliffords, then do the proper CNOT, and then put new encodings on top. So, and then in order to kind of show that this actually worked, player 1 will execute the public authentication test on this state. And I'm cheating quite a bit here because in fact this is really just a high level idea. In fact, the real protocol is quite a bit more complicated because on top of this, we have to, well, just in order to perform this first step, we actually have to send this whole state around. So basically it has to go from player to player, and they all kind of do their share in order to perform this operation. So this will actually require a whole round of quantum communication where both these qubits actually go through the whole players. And again, the reason is basically because how can we trust player 1 to actually do this if he's dishonest? No? So somehow the state has to pass by at least one honest player for this to actually happen. And so we basically have to send it along all the players. All right, so that's the CNOT part. I will move on to the, as long as there's no questions, I will move on to the non-Clifford gate. And in our case, we choose the T gate. It's kind of the square root of the phase gate, or the fourth root of the Z gate. And we resolve to kind of the standard trick in fault tolerant computing, namely magic state computation. So I assume we can actually try to do a little poll. So who has not seen this magic state computation before? So now if I go to participants, I can see who is still awake, and you can press on yes or no. So the question is, who has not seen magic state computation before? And maybe this is not the right question to ask, but it's double negation. Oh, Vinod raised his hand. Okay, Vinod has not seen it before. Very good. There are a few people who say who have not, but just judging from the name, I basically know that most of you have seen this before. I also see blinking more. Ah, there's a chat. Haven't seen magic states before. Okay, great. So magic states are magic, but really they are not. It's not that spectacular. What people call magic states in a quantum case is this. You basically take the plus state. Plus is actually 0 plus 1, like the even superposition between 0 and 1. And if you apply a T gate to it, and the T gate is this thing up here, then that's what we call a magic state. And remember, the goal is that we have some qubits, psi, and we basically want to apply the T operation to it. And this little circuit, what we call magic state computation, does the job. So turns out that if you put in magic states here on the second wire, and you put in your qubit in the first wire, and you apply these operations, you do a CNOT, you measure this, and classically controlled on the outcome, this is 0 and 1, you apply an X and a P, just as some other quantum gates, then it turns out that you have applied the T operation to psi. So this is something you can verify on paper. And that means basically that once we have magic states, we will be able to apply T gates using this procedure. However, remember, we want to do everything in an encoded way in our case. So we'll have encoded states psi, and we also need encoded magic states. And those together, using this procedure, we will end up with kind of encoded states where the T gate has been applied to our data qubit.
So Chris,
yes.
so this is a way to compute the T gate given sort of pre-processed T gate in some sense.
Yes.
Together with the ability to do CNOT X, which is XOR, and a P gate. That's it. That I can take it as a box. Okay.
Yes, exactly. The kind of the magic is why this is what's called magic is that indeed this circuit here are just Clifford operations. So these are kind of from a lower class, and having this additional magic state as resources, which do not depend on the states that you actually want to apply the T gate to, you're able to perform a T gate.
So is this specific to the T gate, or can I do a larger class of computations this way?
Yes, you can. This specific circuit I'm showing here, I mean, these operations here depend on what you want to perform, and also, of course, what you put in here. But there are equivalent ways of doing this also for different kind of resource states. But the point is basically, I think, any gate outside the Clifford group will kind of give you a universal set of for quantum communication.
Okay, got it.
Okay. So there's two questions. How do we get this encoded magic states, and how do we perform this circuit? And so the problem here in this multi-party computation setting is that nobody can be trusted to actually create properly encoded magic states. So what we're going to do is a procedure called magic state generation. So we basically just going to ask one player, say player 1, to generate a lot of these encoded magic states. And then we're going to use some cut and choose technique to make sure that these states are actually good enough. So we just ask player 1 to generate a lot of them. And then we send around this whole bunch to basically the player. Then every player will test n random states of that. And whenever I say random, of course, I mean Shafi is going to instruct them which of the states they should actually test. So whenever we need classical randomness, we're going to get that from the classical MPC. Then this just goes around. Everybody takes n of them and tests. And again, we abort if something is not good. If the tests don't pass, then we abort. We send them all around. Hopefully, we will end up with enough of them at the end. So that's how we've chosen the remaining. We want to make sure that the remaining n copies are pretty good. They're pretty good. I mean that with very high probability, only a small constant fraction of them is not the right state. But what we want to do is actually we want to have one state which is kind of exponentially close to the right state. But for that, there's a procedure called magic state distillation. And this is yet another kind of part of the magic, namely that's only a Clifford circuit. So again, with kind of only operations from our lower class, which we already know how to perform, we can do that on n states in order to distill one state, which now has the guarantee that it's exponentially close to the correct state, to a correct magic state. So this remaining copy will be very good. Again, of course, in the Clifford circuit, there might be randomness, and that's again what we get out of the classical MPC.
So sorry, can you say again what the distillation process does? It takes n states, of which some are guaranteed to be good, and
yes, after this cut and choose procedure, we have the guarantee that only a small constant fraction of these states that remain in the middle are not good, are not the right states. But what we want is we actually want one state of which we know that of which we have the guarantee that it's exponentially good to this encoded magic state.
I see.
So it's just a quantum distillation procedure, again, well known for people who do fault tolerance, because that's also an essential thing in quantum computing. And fortunately, this is it's easy to do. It's in this lower class. It's a Clifford circuit that does this. And it comes with the guarantee that the remaining state then is actually very good in the sense of like exponentially close to the right state. So that's great. So quick summary so far. we have protocols that can perform 1-qubit Cliffords. This we've seen. It's just like updating the key that is remembered by the MPC. You've seen how to do CNOTs. So that's basically asking a player to apply an operation and then send it around and actually perform this public authentication test. Then we have just seen how to do T-gates, namely we do magic state computation and we generate encoded magic states. However, in order to actually perform this circuit, even in an encoded form on encoded states, what we need to do is we need to do this measurement as well. So the last thing, kind of the last missing ingredient that I have to show you is how to do computational basis measurements, because you need that in order to perform this magic state computation. So here is how this goes. So this is the last step of the computation part. So let's say we have an encoded qubit. I just rewrite it in the computational basis. So M is just a single bit. These are the amplitudes of this bit. These are hopefully proper traps, and then Clifford applied on the whole thing. Now what we're going to do in order to kind of measure this data qubit in the computational basis is that the MPC samples a bunch of classical strings, R and S, n+1 bit strings, and C. And then again, Shafi instructs this player to apply a big operation, namely this here. I will parse that in a second. So, so basically it undoes the Clifford. No? So let's get rid of the Clifford. Then we do a bunch of CNOT operations that, whether we do them or not, are dictated by this random string C. And basically just CNOT this kind of data qubit into the traps. And notice if M is 0, then this is not doing anything. And if M is 1, then we basically spreading these ones to some of the traps in here. So that's what this C does, and the CNOT operation does. And on top of this, we basically just apply a one-time pad. So this is just a one-time pad encryption. So random phase and random bit flips. And all this whole package, again, is just given as one big operation to the player as an instruction to apply. And finally, the player measures in the computational basis. And the outcome will be R prime. So this is just the string that comes out. And now the MPC can do a check whether this has been properly performed. Namely, it's going to check whether this R prime that comes out is the one-time pad key. So this is just these bit flips here, this X. So this is this R, XORed with the bit that has been measured. So whether there exists bit, so either 0 or 1. And then you either have 0, 0 in case M is 0, or you have a 1 here if the outcome was 1, and basically C on this part. So because we have been spreading the ones to the traps. So that's the check that the MPC is going to do. Of course, now we have to prove that this actually works, but somehow intuitively this is doing the right thing. So this is how you perform a computational basis measurement state. And now the MPC at least knows the measurement outcome, knows the M. So now it depends, either the MPC can announce that to the players or announce that to the next player that has to perform the computation. Remember, we want to, for instance, we need that in the magic state computation. So here, these conditionals, these outcomes are now known to the MPC. And so the MPC can then tell the player whether they have to apply this X or not, and this P operation. That's how we can actually perform this circuit. All right, I'm close to the end. I see yeah, like 45 minutes, 50 minutes. So time for summary. We have constructed a protocol for multi-party computation of any quantum circuits. Here's a bunch of properties. So we are computationally secure, but as I said at the very beginning, basically we are information theoretically secure modulo how secure the classical MPC is. So that one requires computational assumptions, but we can actually even tie into this pre-processing paradigm. So often classically secure multi-party computation protocols against dishonest majorities are of the form that you do some pre-processing phase where you need computational assumptions. And in order to generate some correlated randomness, maybe authenticated multiplication triples for those who know, and then you can perform information theoretically secure, efficient computation on it once the inputs are known. And we basically tie into that step. So if you can do this first pre-processing step in the classical world, then from then on you actually have information theoretic security even in the quantum case. And we can tolerate up to k-1 cheaters if you have k players in total. Then in terms of efficiency, so our states, basically our encodings are at most of size 2n+1, versus if you do the straightforward generalization from DNS, you would get kn+1. And the T-gate operations we do in order to generate these magic states, in our case, we need like k times n magic states to start with. Whereas if you do the naive extension of DNS, then you would end up with something exponential in the number of players. But to be honest, I mean, they have not analyzed this setting for the multiplayer case. Then, then you have to do a bit of accounting to kind of figure out what the number of communication rounds is. but it's basically k times d in our case. Well, it's d plus log of the security parameter, where d is kind of counting the layers of difficult operations. And in our case, difficult means either CNOT or T, because for both of those, we need kind of to go around the number of players once. And there's a bunch of things you can do in parallel. So you have to kind of sit down and to count a little bit, like what exactly are the things that can be parallelized. But then you will end up with this number of quantum communication rounds. All right, maybe a bunch of open questions. That's my last slide. So the question maybe for Vinod and others, I think Vinod, we've actually already quickly talked about this. Are there post-quantum secure classical multi-party computations protocols that are good for dishonest majority? I think as far as I remember from Vinod, he said, yeah, sure, they exist. Depends on how efficient you want to be. Yes, I think so. When I looked into the literature, there are kind of the most efficient protocols that are actually used in practice use these OT extensions, and they're, I think, as far as I know, only proven in the random oracle model. I don't know if there's also QROM proofs for that, but that's, I think, one of the things that one would have to check. Then yeah, so there's a bunch of kind of technical questions about our protocol. Can you do the CNOT operation? I said for now it requires one round of quantum communication, so we need to send this state around, but it's not fully clear whether this is actually needed. So it might be possible to do this without, so maybe actually have these authentication checks only at the beginning, at the end, so that would save some additional rounds of quantum communication. It's just, we don't see an attack. It's more like our proof techniques at the moment, they don't allow for that. Then the question is, can you get more efficient protocols for more specific functionalities? Now this works for any quantum polynomial time computation, but maybe if you zoom into like more specific class of circuits, then it might be possible to gain efficiency here and there. And I think an interesting question could be like the comparison with classical MPC, which turns out to be a very versatile tool. So not just do MPC for the sake of MPC, but also use it as an ingredient to build other things like zero knowledge proofs or digital signatures. And at least to us, it wasn't like straightforward how this would actually work, and whether such use cases can be translated to the case of multi-party quantum computation. But that's maybe just a lack of knowledge of literature. Maybe some people more familiar or totally familiar with the classical MPC world can chime in here and let us know. Maybe there might be applications of doing this also in the quantum case. All right, thank you very much for your attention, also to the sponsors of this work, and I'm happy to take questions now.
So Chris, the number of rounds is, even if you had the best possible classical MPC protocol, let's say, I don't know, 2 rounds, applause. Okay, yes, virtual applause. Okay. Yeah, even if you had the best MPC protocol classically, you would still need a lot of rounds here, right?
Yes.
Like
so
one for
sorry?
Like one for every T gate, kind of.
Yeah.
Okay.
Definitely.
Got it.
At least for the way we do it, yeah. And we really make heavy use. Basically, it's partly it's because of simplicity. We can just like delegate any classical computation to the MPC, which makes it easier to control, not because it's just assuming a trusted third party. But yeah, it might be possible to kind of reduce the calls to the MPC quite significantly. We haven't really tried to optimize this.
Thanks.
This is a bit of a side question maybe, but these protocols, they never have, like, I think it's related to Dan's question from like abort resistance in a way, like if any, just even one party decides to be unhappy in some of the checks they're supposed to do, then you just quit.
Yes. Yes, so that's what we do. Basically, from the point of view that, yeah, if you cannot get around abort in the case where you have a dishonest majority. But of course, I think in the MPC world, and maybe Vinod can say more about this, there are ways, they're kind of more, I mean, there's like a million different models anyway, but there are kind of more, say, realistic adversary models where you have, first of all, you can look at adaptive adversaries that kind of only corrupt players during the protocol. And then you can also have mixed versions of like you're only allowed to corrupt so many, and then you might get different results about the board. So you can kind of have some partial fairness built in.
But even if you had that for the classical MPC, you'd still have to change your protocol a little bit, like this magic.
Yeah, I guess so. Yeah. Yeah, I would suspect so. Yeah. I don't know, Vinod, do you know whether there's kind of what are natural relaxations of having this abort around?
So there are a bunch. Maybe the other crypto people here would know more. But there's security with the bots. There's fairness, which is a strong condition, and you cannot achieve it with more than half the players being dishonest.
Yeah.
And I guess with honest majority, you can get everything. You can get you can get the best possible world. Yeah, there are a bunch of relaxations. I'm not sure exactly.
Yeah, I guess one would have to look at them in more details. Whether these kind of improvements to the classical MPC are compatible with our extension to the quantum case. I think it's not that generic. Yes, are there any other questions?